Hi everyone. Here we are going to learn about the non-linear support vector machines. As you have seen in the previous video, we covered the linear support vector machines, which is a technique, um, a machine learning technique for doing classification of various data points. So in case of non-linear support vector machines, we do the classification in a different way in comparison to the linear support vector machine. So in case of the data sets having non-linear decision boundaries, the support vector machine model is applied in a different certain way. And the basic idea is to transform the data from its original attribute space in X into a new space. And the new space, we can call it as psi of X, a new distribution, so that a linear hyperplane can be used to separate the instances in the transformed space using the SVM approach. The learned hyperplane is then can be projected back to the original attribute space, resulting in a nonlinear boundary. So here in the picture that you see, some of the points are inside the marginal space or the separator, and this will make difficult in segregating the data points. Let's see the more details about our nonlinear support vector machines. So nonlinear support vector machine, or here the nonlinear transformation, is to make the data set higher dimensional space, that is mapping into a higher dimension. And it is also the fundamental of a nonlinear system, and it in turn reveals a graph in of a nonlinear data set, and it cannot be used using a it cannot be used implementing a linear kernel. Rather than, we should use a different type of kernel, and most often the a specific type of kernel is used in various scenarios, and that is called as your Gaussian kernel. So if you see in the slide, in your nonlinear support vector machines, the basic uh, function for determining the hyperplane, it's basically the wx plus p, but rather than just comparing with the positive at the negative value of 1, we are considering a slack variable as well. So we consider a sample or data point to be positive if w into x plus b is greater than or equals to 1 minus the slack variable. So here this sign is represented as the slack variable, and the negative sample can be determined by the second formula here. So in this way, you can categorize or segregate the data in terms of the positive and the negative samples. And as we always emphasize on minimizing the margin of the hyperplane, if you remember in the linear SVM, in the same way for minimizing the margin, this is the formula which will be used in terms of your nonlinear support vector machine. So the slack variable actually play a major role in the nonlinear support vector machine. And here, if you see the k, this k is considered as a kernel function. Okay, and this kernel function, that is the k value, can be fine-tuned as per the dataset requirement. So while doing the analysis, you have to take a closer look into the dataset, and analyzing properly the dataset, you will choose the value of the k. So let's see a simple data segregation scenario here. Here you see there is a hyperplane, and two marginal hyperplanes are given in the blue colors, and some of the points are passing through the marginal hyperplanes, and some of the points are lying inside the two marginal hyperplanes as well. And there are two types of points that you see, the green points and the blue points. So here the function f is representing the different samples. So the middle hyperplane, it's nothing but your wx plus b is equals to 0, if you remember in case of your linear hyperplane. and for nonlinear, for the negative you have -1, and for positive you have +1. So here any points lying in this section, it is the slack variable is considered as 0. If any point lie here in between this range, the slack variable is considered as less than 1. And for any points lying inside this region, here the slack variable is considered as greater than 1. So in terms of this assumption of the slack variable in different data distribution or the hyperplanes, you have to define your function for categorizing the data set. So let's see um, uh, let's see how to understand a nonlinear support vector machine in terms of a data decision boundary, whether it is linear or nonlinear. So in case of data sets having nonlinear decision boundaries, the SVM is applied in a certain way. And the basic idea is here to transform the data from its original attribute space X into a new data distribution or space, so that a linear hyperplane can be used to separate the instances in the transformed space using the SVM approach. The learned hyperplane is then can be projected back to the original attribute space, resulting in a nonlinear boundary. So if you see in this picture here, it shows an example of a two-dimensional data set consisting of the squares, and here the labels can be y equals to 1, and the circles, and here the labels can be y equals to -1. So the outside data points are considered as positive labels, whereas anything inside this region is considered as negative. And this in this way we separate both the groups in this plane provided here. So instances of the data set can be classified using this equation that you see here. So actually, why do we have 0.5, 0.5? So here we assume the cluster centroid is your 0.5, 0.5. And this formula is nothing but your Euclidean distance. So you calculate the Euclidean distance from a particular point to the cluster centroid. You already are aware about this formula, and it should be greater than zero point 0.2 for categorizing a positive sample. Here we are considering zero point 0.2 due to the consideration of two classes. Here we have blue samples and the red samples. As we have two classes, that is why the formula is formed in this way. Let's see how to transform the data into the higher dimensional space. So you just saw this is the basic formula for a two-dimensional data point in a plane. So actually the previous decision boundary, this formula, it can be further simplified into a quadratic equation that you see here, the first equation. And a nonlinear transformation needed to map data from its original attribute space to a new space, so that a linear hyperplane can separate the classes. So we have a transformation as shown in the second equation. If you want to have a look into a thorough explanation of the derivation of the equations, you can take a look in the book. The whole explanation or the derivation is provided there. Then from the second equation, we can further simplify it using the weights, and it is shown here in the third equation. So further, if we again simplify in terms of a generic equation, the decision boundary will be formed by this formula, the bold formula here. So in the figure, if you see, it shows how the points are transformed in the transformed space have been arranged, where we can see that all the circles are located in the lower left hand side of the diagram. So this is the transformation of the original data distribution or space to a higher dimensional space. Let's see different types of kernel functions that we just discussed in our nonlinear SVM. So SVM algorithms use a set of mathematical functions which are defined as kernel. The function of kernel is to take data as input and then transform it into a required form. So different SVM algorithms use different types of kernel functions, and these functions can be of different types. So some of the function types mainly often those the functions those are often used are provided here: the polynomial, radial basis function, and sigmoid. Um, so kernel functions actually introduce for different set of data such as graphs, texts, or images, and most of the time the data are provided in the format of vectors. And the most used type of kernel function is your Gaussian radius basis function RBF. Why it is often used? Because it has localized and finite response along the entire x-axis. The kernel functions return the inner product between 2 points in a suitable feature space. Thus, by defining a notion of similarity with little computational cost, even in very high dimensional spaces. Here, if you see the kernel function, each of them has different parameters. The xi, xj are nothing but the two-dimensional points, and the polynomial kernel is provided in this formula here, where h is nothing but the degree of the polynomial used in the equation. Then in the radial basis function, Gaussian radius basis function, it is a exponential. The equation is in the form of exponential, and here the sigma is actually nothing but your Gaussian parameter, and here it is always considered greater than 0. And the sigmoid kernel is always provided in terms of a tan function. Here, if we again more in a more simpler way, if we want to try to understand the kernel trick of nonlinear SVM, so for a kernel function k of xi xj between two instances, that is xi and xj, it can be defined by the first formula here. Okay, and some of the examples are provided here. The first one is your polynomial, second one is your Gaussian radial basis function, third one is your sigmoid function. This is your kernel trick. Let's see one example of the polynomial distribution or the polynomial kernel. So here actually it represents the similarity of vectors in a training set of data in a feature space over polynomials of the original variables used in the kernel. So intuitively, the polynomial kernel looks not only at the given features of the input samples to determine their similarity, but also combinations of this. So although the RBF kernel, that is the radial basis function kernel, is more popular in SVM classification than the polynomial kernel, the latter is quite popular in a different type of analysis, that is or task which is called as natural language processing. And the most common degree that is used for this purpose is your quadratic, and here the degree is always considered in terms of 2. And why we don't consider more higher degrees? Because they tend to overfit the NLP problems. So in this polynomial kernel example, you can see how the hyperplane distribution is provided and how effectively it is able to classify the data. But there are certain points in this region which are not correctly classified or misclassified, and they can become outlier for some reason here. So there are different ways of adjusting or balancing the degree to get more efficient analysis. So if you see in this position, for h equals to 3, that is the degree is 3 for this polynomial kernel. Here some of the blue points are merging over to the green side, so which is not correct. But again, if you increase the degree of the polynomial kernel, then those blue points will be correctly classified, and they are classified in the blue region here. So even if you change the degree of the polynomial value, the classification changes to certain extent. So now let's see why SVM is effective on high dimensional data. So there are a set of algorithms called kernel methods which are used to implement the nonlinear classification. And SVMs are always well known for their effectiveness in high dimensional space, where the number of features is greater than number of observations. The model complexity is of order of n number of features and the square of number of samples. So it is perfect for working with data where the number of features is bigger than the number of samples. So always we rely on the number of support vectors in order to understand the complexity of the training data set or our training classifier. And as we have various support vectors, they are really meaningful for correctly training the data set and defining the decision boundary. Some more advantages why it is applicable on high dimensional data. Um, so SVM is a kind of large margin classifier. It is a vector space based machine learning method where the goal is to find a decision boundary between two classes that is maximally far from any point in the training data. The terms support vectors, which are most essential, they refer to the coordinates of the individual observation. Support vector machine is a frontier which best segregates the two classes using a hyperplanar line. These are some of the advantages. So some of the more equations defining the optimization problem. Mm, Then what are the different disadvantages or issues with our or limitation with our nonlinear SVM? So here the main issue is that sometimes it is a little bit complex to define the mapping function, and while defining it into or transforming it into the high dimensional space, the computation is also complex. And in terms of it, it gives us a view of curse of dimensionality. Even if we can transform the data into higher dimensional space, but balancing it out or handling it, it's really difficult. Okay, so this is all about our nonlinear SVM. Um, so please go through the slides and also look at the derivations in the book if you want to have a clear picture of the derivation, how the formulas are defined, and then let me know if you have any questions.